Hey everybody, and welcome back to AI.Code.Cast. You know we love to bring you a fresh coding challenge every single day.
Absolutely.
And today's is a real head-scratcher.
Hmm.
It's called valid arrangement of pairs.
Oh, yeah, this one's a good one.
So basically, we get a set of number pairs, and we have to
Hmm.
figure out if we can arrange them in a way that...
Kind of like a chain, right?
Exactly. The second number in each pair has got to match up with the first number of the next pair.
It's kind of a fun little logic puzzle, and it actually ties into some cool concepts from graph theory.
That's right. All right, so let's break this down a bit further.
Okay, sounds good.
Let's say we got this set of pairs. 5, 1, 4, 5, 11, 9, 9, 4, and 9, 4 about.
Okay.
Our mission is to find some order where these pairs connect up nice and smooth to form a continuous chain.
Like puzzle pieces, but with numbers instead of shapes.
I like that analogy. Now, thankfully,
Oh, and this is important.
yeah,
This problem guarantees that there's going to be at least one valid arrangement for any set of pairs they give us.
well, that's good to know. At least we're not chasing wild geese here.
Right. Exactly.
But the question is, where do we even start? Well, I mean, could we just randomly shuffle these pairs around until something clicks?
You could. That's what we call the brute force approach.
Brute force, huh?
Yeah, basically, you're trying every single possible arrangement until you stumble upon one that works.
I could already see how that could get messy.
Oh, yeah. Especially when you start dealing with larger sets of pairs.
Right. It's like trying every key on a giant key ring, just hoping to find the one that fits the lock.
Exactly. And the more pairs you have, the more those possibilities just explode.
So brute force is probably not the most elegant solution here.
You got it. We're going to need something a bit more clever.
A smarter approach.
Exactly. An algorithm that can guide us towards the solution without having to exhaust every possible combination.
Okay, so brute force is out.
Right.
But what are our other options? Are there any hints hidden within the problem itself that could point us in the right direction?
Let's put on our detective hats and see what we can find. What jumps out at you about these pairs and the condition that needs to be met?
Well, each pair is linking two numbers together, like forming a connection between them.
Interesting.
Could that be a way to visualize this problem?
You're on to something. What if we stopped seeing these as isolated pairs and instead thought of them as connections between these numbers?
Like a network.
Yeah, exactly. Imagine each number as a point, and the pair represents a line connecting those points.
So we're starting to talk about a graph now.
Mm.
Each pair tells us how the points in this network are connected.
Precisely. And this shift in perspective from just pairs to a graph can give us some powerful insights.
But how do we actually use this graph to find the right arrangement?
Let's focus on the core requirement for a second.
Okay.
The second number of a pair needs to match the first number of the next.
Right.
If we were building this chain step by step,
Yeah.
what would we be looking for when choosing the next pair?
Well, we need a pair where the first number is the same as the second number of the pair we're currently holding, like finding the right puzzle piece that fits.
Precisely.
So at each step, we need to quickly find a pair that fits with the current one based on their numbers.
You got it. Now here's another challenge.
Okay.
How do we keep track of which pairs we've already used?
We don't want to get stuck in a loop picking the same pair again and again, right?
Exactly. That's where a data structure like a stack could come in handy.
Okay, a stack.
Think of it like a pile of papers. You can put things on top and take things off the top.
So we could use the stack to store the pairs we've already used.
Right.
But even with a stack, how do we find that next fitting pair without having to search through all the remaining pairs every single time?
This is where things get really interesting. In our graph representation, each point or node has these two key properties, in degree and out degree.
Right. The in degree tells us how many connections are coming into a node, and the out degree tells us how many connections are going out. But how does this help us solve our puzzle?
Well, imagine you're standing at a node in our graph.
Okay.
The out degree tells you how many potential next pairs you have available.
I see.
And the in degree tells you how many previous pairs have led to this node.
So by looking at these in degrees and out degrees, we can get a sense of how many times a number appears as the starting or ending point of a pair.
Exactly. And that information can be super helpful in guiding us to build a valid arrangement.
Like if you're at a crossroads and you know one path leads to more options further down, you might choose that path.
Precisely.
Okay, I think I'm starting to see the light here.
Good.
These in degrees and out degrees are like signposts in our graph, helping us choose the best route to build our chain.
You're getting it. And this leads us to a powerful algorithm that uses these graph concepts to solve the valid arrangement of pairs problem efficiently.
All right, I'm all ears. Tell me about this algorithm and how it brings all these ideas together.
Okay.
But first, a super quick recap.
Yeah.
We ruled out brute force. We're visualizing our pairs as a graph.
Yes.
And we've discovered that in degrees and out degrees can give us some valuable clues.
Absolutely.
So what's next?
Well, let's dive into Hierholzer's algorithm. It elegantly uses these graph properties to find a valid arrangement. So Hierholzer's algorithm is all about finding what we call an Eulerian path in our graph.
An Eulerian path.
Yeah, think of it like taking a walk through our network where you visit every single connection exactly once.
Okay, so it's kind of like those puzzles where you have to draw a shape without lifting your pen from the paper.
Exactly. You're trying to find a route that covers every line without retracing your steps.
So in our case, instead of lines, we have pairs of numbers, and the connections are dictated by those number relationships.
Right.
So a Eulerian path is basically a sequence of pairs that includes every single pair once and only once, and meets that condition that the second number of one pair matches the first number of the next.
You got it. And Hierholzer's algorithm gives us a systematic way to find this path.
Okay, I'm ready for those steps. Lead the way. What's the first move?
Well, first part we've already done, building our graph.
Right.
Each unique number in our pairs becomes a node in the graph, and each pair represents a connection or an edge between those nodes.
So for our example, set 5, 1, 4, 1, 11, 9, 7, 9, 7, 4, we'd have nodes for the numbers 1, 4, 5, 9, and 11.
That's right. Now the next step is figuring out where to start our walk, our Eulerian path.
I have a feeling this is where those in degrees and out degrees come into play.
You are absolutely right. To find a good starting point, we need to look for a node where the out degree is exactly one more than the in degree.
So we want a node that has one extra connection going out compared to connections coming in.
Yeah.
Why is that so important?
It's like starting our walk at a point where we have an extra path to take, ensuring we can move forward without immediately hitting a dead end.
That makes sense. But what if there's no such node? What if all the nodes have the same number of in degrees and out degrees?
That's an interesting scenario. In that case, our Eulerian path actually becomes an Eulerian circuit, meaning we'd end up back at our starting node after visiting every edge. We could start at any node.
Okay, so we've got our graph. We found our starting point.
Yeah.
But how do we actually traverse this graph to find that perfect Eulerian path?
That's where a search algorithm called depth first search, or DFS, comes in.
DFS.
Yeah, imagine you're exploring a maze. You pick a path and you just keep going as far as you can.
Okay.
If you hit a dead end, you backtrack and try a different path.
So we're systematically exploring our graph, trying different paths, until we find one that covers every edge exactly once.
Exactly.
But how do we keep track of which edges we've already visited? We'd want to go in circles.
Exactly. That's why, as we explore the graph, we remove each edge we use from our graph.
Because we're like marking off a path on a map so we don't accidentally retrace our steps.
Exactly. It's like we're burning bridges as we cross them.
I like that analogy.
Now, here's the really clever part. As we backtrack during our DFS, we add the nodes we visited to our solution path, but in reverse order.
Why in reverse order? Wouldn't that mess up the whole arrangement?
It might seem counterintuitive, but think about how DFS works. We're exploring as deep as possible before backtracking.
Okay.
So the last nodes we encounter during DFS are actually the ones that should come first in our final arrangement.
So it's like we're retracing our steps and building the path from the end back to the beginning.
Exactly. By the time we've backtracked all the way to our starting node, we'll have a complete Eulerian path, and that's our valid arrangement of pairs.
Wow, that's pretty clever. So Hierholzer's algorithm uses DFS to systematically explore the graph, and by cleverly backtracking and reversing the order, we get our solution.
Yeah.
But how does this compare to that brute force approach we talked about earlier?
The beauty of Hierholzer's algorithm is that it's way more efficient. Remember how the number of possible arrangements just explodes with brute force? With Hierholzer's, we only visit each edge in the graph once, making it much faster, especially when we have a lot of pairs.
So it scales much better than brute force.
Exactly.
That makes sense, especially for real-world scenarios where you might have hundreds or even thousands of pairs.
Right.
But is Hierholzer's algorithm the only way to solve this problem? Are there any other approaches we could explore?
You're always thinking ahead. There are other algorithms for finding Eulerian paths, each with its own unique way of approaching the problem. Well, one alternative is Fleury's algorithm.
Okay, Fleury's algorithm.
Yeah, instead of just removing any edge as we go, like in Hierholzer's, Fleury's is a bit more picky.
Picky.
Yeah, it really tries to avoid bridges.
Bridges.
Yeah, think of a bridge connecting two parts of our graph.
Okay.
If we remove that bridge, those parts become disconnected, right?
Yeah, we'd split our graph into separate islands.
Exactly. So Fleury's algorithm makes sure we don't burn those bridges too early.
I see.
It carefully chooses which edge to traverse next to avoid disconnecting the graph.
So it's a bit more cautious than Hierholzer's,
Yeah.
like choosing our steps carefully so we don't get stranded somewhere in the graph.
Exactly. It's cool how different algorithms can approach the same problem in totally different ways.
It's like having different tools in our problem-solving toolbox.
Yeah.
We've got the bold and efficient Hierholzer's algorithm,
Right.
and then we have the careful and deliberate Fleury's algorithm.
That's a great way to put it.
Okay, so we've explored a couple of ways to solve this valid arrangement of pairs problem, and both involve thinking about pairs as connections in a graph.
Right.
But why should anyone care about arranging pairs in a valid sequence?
That's a great question. It might seem like just a theoretical puzzle, but it actually has applications in a lot of different fields.
Really? Like what?
Well, think about scheduling.
Right.
You've got a bunch of events, each with a start and end time.
Yeah.
How would you arrange them so they don't overlap?
I see where you're going with this.
Hmm.
Each event could be represented by a pair, the start time and the end time.
Right.
And finding a valid arrangement would give us a schedule where no events conflict.
Precisely. Or think about planning a route.
Okay.
You have a list of locations you need to visit.
Yeah.
What's the most efficient way to visit them all?
Our pairs could represent the starting point and the ending point for each leg of the journey.
Right.
And a valid arrangement of those pairs would give us the optimal route.
Exactly. These are just a couple of examples, but the idea of finding a continuous sequence based on connecting pairs pops up everywhere. Logistics, network optimization, even bioinformatics.
Wow, so this seemingly simple problem has connections to so many real-world scenarios.
It's amazing, right? That's the beauty of computer science. It gives us these tools and ways of thinking that apply to problems way beyond just coding.
All right, so to wrap things up today, we've explored the valid arrangement of pairs problem.
We sure have.
We talked about how brute force can get really inefficient, and then we dug into Hierholzer's algorithm and even touched on alternatives like Fleury's algorithm.
And we've seen how this problem, though it might seem abstract, has some pretty practical connections to the real world.
If you're listening and want to dive deeper, I encourage you to check out AI.Code.Cast.
Absolutely.
We provide all the source material, including code implementations in various programming languages.
And here's a final thought to ponder. What if, instead of pairs of numbers, we had groups of 3 or even more?
Well, that's interesting.
How would our algorithms need to change to handle those more complex connections?
That's a great question to leave everyone with. Keep those coding brains engaged, and we'll catch you on the next AI.Code.Cast.